Hi, I'm Vincent Bassett. I'm a senior mechanical engineer.
Hi, I'm Kyle Beatty, Senior Electrical Engineer.
Hi, I'm Jonathan Kors, Senior Mechanical Engineer.
I'm Gustav Eriksson, Senior Mechanical Engineer.
Our motivation is that there's no attitude control for nanosats to be sent into outer space. A miniaturized liquid gyroscope will have the precision and accuracy that a traditional gyroscope will not achieve. This is due to friction loss and ability to manufacture these traditional gyroscopes. The idea is to use liquid rather than a traditional spinning rotor. Here, we are demonstrating a superconductor to float a magnet with ferrofluid coating it. This will represent a liquid gyroscope in outer space. We can see that applying a force allows the blob to rotate. The objective is to design, construct, and test a miniaturized moving liquid gyroscope prototype, using ferromagnetic fluids capable of demonstrating classic gyroscopic motion and behavior. Our final result is to suspend the blob and rotate it in a three-dimensional plane.
The original solenoid design was a single layer of wire with 50 turns. To increase the field strength while decreasing the current, we increased the turns by a factor of 3 using Ampere's law to calculate the number of turns for the desired electromagnetic field strength. This resulted in a 3-layer solenoid. The layering was a product of the constrained length of the solenoid.
Here's our cubic gyroscope design. First, we have the stand, which holds the gyroscope in place and also has a cup that holds the ferromagnetic fluid blob. Here are our 12 poles, which are all triple wrapped and heat shrunk. These poles are supplied with current, which creates a magnetic field which controls the ferromagnetic fluid blob. These are our corner pieces, which allow for easy assembly and disassembly. Here you can see our ferromagnetic fluid blob, which consists of a spherical magnet and ferrofluid.
The wiring of the poles leads back to a breadboard. The breadboard allows us to control the direction in which the solenoid will point. This is done by switching the leads of the solenoids. The breadboard is then connected to a circuit structure. The circuit consists of a rectifying diode, resistors, and transistors. There are 6 isolated circuits to control 6 directions of the poles. The Arduino Uno will supply current to turn on the transistor, which then amplifies the current to 2.56 amps supplied to the solenoids. Here we have the blob rotating at 24 frames per second. The blob is transitioning along 3 different planes while maintaining 2000 RPMs. Each pole pair is pulsating at 33.3 Hz and are 120 degrees apart from each other. Essentially, we would want to minimize the angle of separation between the poles and increase the pulse frequency to maximize control of the blob. We will now break down this rotation with a high-speed camera.
Here we see the gyroscope under a high-speed camera at 500 frames per second. It begins with an unsteady rotation as it begins to accelerate, attempting to match the frequency of the pulses from the poles. As it gets up to speed, it is apparent that the rotation has become much steadier. The blob is rotating at a 45-degree angle from the horizontal. Here, it transitions to a vertical plane, resulting in another transitional period followed by a mostly steady rotation. There is a slight pause visible in each cycle. This is an undesirable effect that could be eliminated with further design refinement. The reason for the instability is that in order to create vertical rotation, poles from 2 different planes are pulsed simultaneously, each pulling the blob in a different direction, the vectors summing to create the vertical rotation. Now, it switches to a 3rd plane, again 45 degrees from the horizontal. It can be seen to go through another transitional period here with very unsteady rotation before again resuming its steady motion.
Levitation is achieved from a stable electromagnetic field. The ferrofluid has a bipolar spherical magnet at the center. As current flows through the paired solenoids, the magnet and the fluid align with the electromagnetic field created. The air gap, which is the distance from the end of the solenoid to the ferrofluid, was a major concern during the early design of our gyroscope. Having the poles facing inward reduces the air gap to a minimum value and concentrates the EM field on the fluid just millimeters from the end of the solenoid, which is the strongest part of the field. We were able to create an EM field that was large enough to achieve complete levitation of the fluid in gravity.